Welcome back to today's video, and I would like us to look at this question on electrodynamics. And this is one of those questions that relate us to uniqueness and boundary condition theorem. And here we are given this question. We are to show that the potential is constant inside an enclosed, completely surrounded by conducting material, provided there is no charge within the enclosure. So here we are looking at this theorem. Of course, it will refer you to basic understanding of what we mean by electrodynamics. So when we talk about the uniqueness theorem, it states that if we can find a solution that satisfies Laplace equation and the boundary condition, that is V is equals to V naught, and then it means that will be the only solution. This Laplace equation is more extensively discussed in real analysis and even in complex mathematics, but here in physics we tend to investigate what happened around that surface because V must be equal to V naught, and that is all we need here in this question in order for us to show that the potential is constant inside an enclosure completely surrounded by conducting material. I remind you, your friend Augustine Gallagher. Stay tuned at this video, and at any point in time you can pause the video, try going into yourself. Of course, I will be doing some proving, and after then we will dive into computation. Stay tuned. So for us to show or to prove that the potential is constant inside an enclosure, we need some things, and let me show you in a while what you need to do. The potential on the cavity wall is some constant V naught, and you must pay attention to this because according to the boundary theorem, it helps us to understand that V must be equals to V naught on everywhere. So it is everywhere. So the potential on the cavity wall is some constant V naught, and I'll prove that to you. And another thing you need to know as we dive into this proving is that the potential inside a function that satisfies Laplace equation and has the constant value, which is V naught, at the boundary V is equal to V naught everywhere. So it is not just at some point. In every part of this Laplace equation, it must be equal to V naught. So you have to pay attention to that. The uniqueness theorem also guarantees that this is the only solution. There is no other solution. It guarantees that this is the only solution. And this also follows that the field inside an empty cavity is zero. So if the field inside that an empty cavity is zero, then V must be equal to V naught. And this is what we'll be going through this evening. Let's see how that goes, as now we want to show that it is really indeed constant, because we are trying to show that the actual value that we are looking for in this case is constant. Okay, so the very first thing we need to know is that the first uniqueness theorem also obeys Poisson's equation. We know Poisson's equation. So if we assume there is some charge inside that region, let's pick a pen in this case. Let's pick our pen. Let's use white color pen, and I want us to assume that there is some charge inside that region. So if there is some charge, we can say that del squared V1, because we are trying to look at every boundary according to the uniqueness theorem, and this will be equal to 1 all over epsilon naught. Of course, multiply this by rho. If we multiply, let's call this the first boundary. So let's go to the second boundary. Let's say that the second boundary is some change del squared V2, and this del squared V2 is also equal to 1 all over epsilon naught multiplied by some rho. So bringing these things together, we are going to have the first one, which is del squared V1. Let's say we want to take this del squared V1 and del squared V2. So what will be our the third one? So let's call this now V3. So let's call this V3, and this will be equal to del squared V1 minus del squared V2. Del squared V2. This will give us, applying the negative sign, when we distribute this negative, we will have negative 1 divided by epsilon naught rho plus 1 divided by epsilon naught into rho if we multiply by this rho. From basic mathematics, we know that minus 1 plus 1 will simply give you 0. So here we are having minus 1 divided by epsilon naught multiplied by rho plus 1 divided by epsilon naught multiplied by rho. This will simply be equal to 0. So what this tells you now is that the difference like in V3 will be nothing but V1 minus V2. It is V1 minus V2, and this actually satisfies the Laplace equation and is 0 on all the boundaries. So in every boundary where you reach, it must be equal to 0. So therefore our answer to this question could be that V3 is equal to 0. That implies that V1 is equal to V2, and that's why we are saying that the potential is constant inside an enclosure completely surrounded by conducting material, provided there is no charge within that enclosure. So V3 is equals to 0, V1 is equals to V2, so it is constant. And this is all you need to show in this video. I remain your humble friend, Augustine Karagai. See you in another video.